The idea of airborne wind energy is to take the good parts of conventional wind turbines and produce a better wind power solution. This is a typical power curve for a wind power system. A Weibull plot shows the percentage of the time, equivalent to the number of days per year, for each wind speed at the site. Capacity factor is the percentage ratio of the actual energy generated over the year versus the maximum possible energy it could generate at the rated power for the whole year. The SkySail's yo-yo kite system reels out the tether in figure 8 loops to generate power, then reels the kite back in and repeats the cycle. With the same size generator, the SkySail system produces less power than a conventional wind turbine in the same wind. The later cut-in lowers the capacity factor and combines to lower the annual energy production. The Makani Flygen kite system flies circles at a fixed tether length. The generated power is sent to the ground via the tether. With the same size generator, the Makani system produces less power than a conventional wind turbine in the same wind. Most of the time, power is consumed, resulting in a negative capacity factor and no annual energy production. The bigger Makani M5 was never built. This is the estimated M5 power curve, a net power consumer for the year. The cubic power curve for a multi-megawatt AWE system consumes more power than it generates over a year, resulting in a negative capacity factor and no annual energy production. The linear power curve never generates power for a complete loop, resulting in a negative capacity factor and no annual energy production. Airborne wind energy systems produce a higher rated power with a cubic power curve, using a thick tether, but generally thin tethers are preferred for lower system costs. Why are airborne wind energy and conventional wind turbine power curves different? The yo-yo tether reel in phase consumes power for part of the cycle. The reel out power generation is erratic. The average power output is much lower than the generator's maximum power. The Makani Flygen power output is erratic around the loop. The average power output is much lower than the generator's maximum power. The law of conservation of energy determines the effect of gravity on the loop in the form of the exchange of potential energy and kinetic energy. When reaching the maximum kite speed on the descent, the kite has to be slowed down by removing kinetic energy. This energy has to be paid back later on the climb. The conversion losses from these transfers determine the energy lost per cycle. In no wind, the kite descent is already in D power at the maximum tether tension. As the wind speed increases, the aerodynamic energy increases until it matches the kinetic energy lost and cutting occurs. More wind increases the aerodynamic energy and power output until reaching the maximum power output on the descent and rated cycle power. Higher winds force a lower wing performance and pattern deformation. At some safe limit, the kite lands and cutout occurs. In order to reduce the kinetic energy lost, the design maximum kite velocity could be increased closer to the maximum kinetic energy loop velocity. This leads to more tether tension and a thicker tether, resulting in a bigger overall system size and higher costs. Generally, a thin tether is chosen. Airborne wind energy extracts much less power from the wind it sweeps. It leaves much of the wind zone untouched, and power per space is reduced. All kites scale up in roughly the same way. Mass increases faster than area. Similarly, the tether mass to area scales with the cube square ratio. The wing loading is proportional to the loop size, and hence the kinetic energy loop velocity. Looking at the Makani scale-up, the maximum kite velocity is much lower than the kinetic energy loop velocity, resulting in a large kinetic energy payback using more aerodynamic energy, giving a delayed cut-in. When scaling up the kite area, the potential energy and the kinetic energy increase faster than the aerodynamic energy. Airborne wind energy scale-up has a dramatic effect on the power curve. More and more of the aerodynamic energy is used to pay back the increasing kinetic energy lost, and not to generate power to the grid. The number of days of the year that consume power gradually increase until reaching a negative capacity factor. At this point, the airborne wind energy system stops being a power generator and becomes a power consumer. The effect of wing loading on an airborne wind energy system. The wing loading determines the turn radius and loop height, and the kinetic energy loop velocity follows from the law of conservation of energy. The difference in loop velocity and maximum kite velocity determines the kinetic energy removed on the descent, and the conversion losses give the kinetic energy lost per cycle. The aerodynamic energy has to replace the kinetic energy lost instead of generating power to the grid, so pushes the cut-in to higher wind speeds. This reduces the capacity factor, annual energy production, and increases the levelized cost of energy. A comparison of the electricity generation costs for an airborne wind energy system and a conventional wind turbine system. The higher wind speeds are negated by more drag from the longer tether, and power output remains the same. Flying tighter loops using higher performance wings should mean a lower cut-in and a higher power output. Wing loading dominates loop size and power output. So, how does airborne wind energy compare to large-scale conventional wind turbines? Small-scale airborne wind energy fails on every metric, and scale-up is even worse. Small-size prototype airborne wind energy systems have a higher power-to-weight ratio than large-scale conventional wind turbines. Small-size prototype airborne wind energy systems have a higher power-to-weight ratio than bigger airborne wind energy systems. Airborne wind energy scale-up fails, but scale down works. This is a review of the published SkySails power curve. Only one reference wind speed at 200 metre altitude was used for all figure 8 loops reeled out to 400 metre altitude. Due to wind shear, the wind speeds are different at altitude. The measured power curve is shifted left from reality, giving it an inaccurate better performance. The estimated power curve is shown.